Paris North, and he will present a talk, a continuous time version of the Derrida-Retaux model.
Okay, well, so thank you very much for the introduction. So indeed, I will present you this joint work with Yunu, who's currently also at Sorbonne Paris Nord, so formerly Paris 13, and Michel Pain, who is at NYU as a postdoc. So the Derrida-Retaux model is a very simple recursion equation. So you start at time 0 with a non-negative random variable. And to construct the random variable at time 1, what you do is you generate two independent copies of X node, you add them together, you remove one and then take the positive part. And you keep doing this for all time. So to get the random variable, well, the law of the random variable xn plus 1, you generate two independent copies of xn, you add them together, then remove one and take the positive part. And the main question related to the Derrida-Retaux model is what can be said about the asymptotic behavior of xn as n grows to infinity. So before discussing a little bit what we did, which was introduce a continuous time version of the model, I would like to talk a little bit about the motivations behind this model. So the motivation for physicists to study this model comes from the pinning models, which is a way to obtain a statistical mechanics model for a DNA molecule. So if you have a DNA molecule, so it's a very long chain of molecules, right? That can be bounded together by pairs. And so when you try to split it, what happens is that sometimes you have to pull quite strongly to put them apart, and some other part it just goes along like nothing, like there is nothing bounding them. And so the model that was proposed was you take a path like this, so Sn, where you can jump by +1 or -1, or if you're at position 0, you can also go straight. And you put RID bounding energies on the edges of the wall, so on the edges of the bottom wall. And you define the energy of a path to be the sum of the bounding energies of all the edges on which it sticks. And so you can define a polymer measure, which is this quantity here. So it's you sample a path proportionally to the exponential of the energy of the path. And so this model is quite general because you can have positive omega i's that attract the strands of DNA one to the other, or omega I negatives that repulse the two strands of DNA. So if omega I is negative, then the strands, they really don't want to share that particular edge. So there is a nice monograph on this kind of models in the book by Giacomin. Okay, so a question related to this polymer model was, so how does this polymer looks like on a large scale? And so you can imagine two distinct behavior. Either it will stick quite closely to the wall, or it will invade the whole space somehow. And so the difference in behavior, you can see it by studying the free energy of the model. The free energy is this limit of the exponential growth rate of the n. The n is the normalizing constant in the polymer measure. And if this free energy is equal to log 2, then you expect to be in the unpinned phase. So you expect the path to look like a random walk, more or less, that has very few interaction with the boundary. Whereas if f of omega is strictly smaller than log 2, then you expect that it only contains a very small portion of the whole space, and it has to be very closely connected to the boundary. And the open problem here is to find for which random variables omegas is the model in the pinned and unpinned phase, and to find the behavior of the free energy around that phase. So this model is this problem is quite complicated. So simplification of the model was proposed in 1992, where instead of looking at the path on the grid, you look at the path on a hierarchical lattice that is described as follows. So you start with an integer, and at stage 0, your graph is just a unique edge. And to get the graph at stage k, what you do is that every edge, you divide it into b couple of edges. And you put your bounding energy only on the smallest edge. So this makes a much simpler model to analyze. So, okay, here's the graph. So you start at the 0 stage with just one edge. So it's not a very interesting graph. And to get the graph at the first stage, what you do is you replace this edge by b couple of edges. So here, b is equal to 3. So I replace it by 3 couple of edges. And you see that the bounding energy, they are all on the bottom pair of edges, right? So the path, it can either go through the bottom way, or through the middle way, or through the high way. So now to get to the second stage, I replace every edge that I had in my previous graph by 3 pairs of edges. And again, you see that the number of paths increases. But the interesting thing here is that, well, to the path at the second stage, well, either it goes through the first little bit, omega 1,1, omega 1,2, which correspond to a graph at the first stage, or it goes out, and then it means that it will never see the boundary of the tree. So you have really this hierarchical structure over here that makes the computation of the free energy quite easy. So here is the graph at the third stage. And so due to this nice hierarchical structure, you get the following recursion equation for the free energy of the process. So zk is the sum of the energies of the exponential of the energies of all paths at stage k normalized by b to the k. And you have the following recursion equation. So zk plus 1 is a product of 2 independent copies of the free energy at stage k plus b minus 1, everything divided by b. And so you're still interested in the free energy over here, that's the limit of 1 over 2 to the k log zk. So there has been numerous results on that model, but the question of the phase transition around around pinning is still open in the most general case. Okay, so Derrida and Retaux, to simplify even further this model, they propose the following. So if you look at log of zk, you see that its recursion equation is really x bar k plus 1 is the log of the exponential of x bar of k1 plus x bar of k2 plus b minus 1 over b. And well, if you can replace the function that log e to the x plus b minus 1 over b by the maximum between x and minus log b. And if you replace the blue function by the orange function, you expect the phase transition to behave very similarly, but the model to be simpler. And indeed, you get the recursion xn plus 1 equal sum of 2 independent copies of xn minus 1, and you take the positive part. So now the analogous of the free energy will be the limit as n goes to infinity of the expectation of xn divided by 2 to the n. And if you start at time 0 with a random variable that is direct mass at 0 with priority, that is equal to 0 with priority p, and with priority 1 minus p is some other priority distribution, then you can define a one parameter family of processes, and you can study the behavior of f infinity of p. And you can say that, well, this function, it has to be decreasing, right? Because you put less and less mass at the initial time. So it means that you have a parameter PC at which you're positive if P is smaller than PC, and you're equal to 0 if P is larger than PC. And Derrida and Retaux conjecture that if PC is strictly positive, then the free energy around this parameter, this critical parameter PC, behaves as e to the minus c over p minus pc to the 1/2. So it means that you have a very smooth phase transition over here. The free energy has infinite derivative everywhere. And so you don't have like a first or second order phase transition. So the transition is really, really smooth. Okay. So just a quick remark that the recursion equation is an equation in law. So far, I didn't talk at all about a process, a Derrida-Retaux process, right? It's just you take at every stage 2 independent copies of the random variable xn. But there is a natural way to describe the Derrida-Retaux model, and it is to describe it on a tree. And if you do it on a tree, then you recover a previously studied model, the model studied by Collet, Eckermann, Glaser, and Martin, where they start with integer valued random variables. So there they consider a binary tree of height n, and they put independent copies of x node on every leaf of that tree, and define the values at internal nodes by doing the sum of the value on the 2 children, -1, and then you take the positive part. So it looks something like this, right? You put ID random variables on the leaf of your tree, and then you make the a plus b minus 1 positive part. So you get something like this, right? So 2 plus 0 minus 1 is 1, 0 plus 0 minus 1 is -1, so you take the positive part, you get 0, and you can make the process flows. So what is interesting is the value at the root for large values of the height of the binary tree. And this can really be seen as a parking process if you replace the internal nodes of the tree by parking spots and the leaves by cars. And if you do this, you say, okay, my cars, they start on the leaves of the tree and they drive towards the root and they try to park in every available parking spot. So if I have, for example, 4 cars that try to come into one parking spot, then one of them will park and the remaining 3, they will have to go down. So the number of trees that leave the parking spot without parking is exactly the variable xn that we're interested in. So we can make the car park and look at the total number of cars that have to leave the tree. And this is the analogous of our variable xn. Okay, so Collet, Eckermann, Glaser, and Martin studied this process and obtained very nice results on condition for the free energy to be equal to 0 or strictly positive. And so they showed that the free energy is equal to 0 if and only if the expectation of 2 to the x node is finite and the expectation of x node 2 to the x node is smaller or equal than the expectation of 2 to the x node. And they did it by studying the moment generating function of xn and showing that it satisfies a nice recursion equation. But importantly here, their result and their method only works for integer valued random variables. If instead of x node being integer valued, we take x node taking value in half integers, for example, it doesn't work anymore. And we have no idea what an analogous of the integrability test for the detection of the f infinity equal to 0 or strictly positive should be. So another point for sure is, well, can we show the Derrida-Retaux conjecture on the behavior of the free energy around the spinning phase transition as well? So can we show that this free energy behaves as e to the minus 1 over p minus pc to the half? So this result has been recently proved by a huge team, so Chen, Dagard, Derrida, Hu, Lifshitz, and Xi. And they showed that under some additional integrality condition, x cubed 2 to the x mu of dx finite, then indeed you have this very smooth phase transition at the critical parameter. But the argument is just that it's exponential minus p minus pc to the power half plus a little of 1. So it didn't get the constant in front of e to the minus p minus pc to the half. And they also showed that this integrability condition, this additional integrability condition is necessary in such a way that you can construct measures so that, well, when the integrability condition fails, then PC is strictly positive, but the free energy does not behave as e to the minus p minus pc to the minus a half. Okay, so what we did with Jun Hu and Michel Pin was to try to find an even further simplification of the model. So something that would allow us to make the computations explicit. So we started with a paper of Derrida and Retaux, that wrote that a good renormalization of the Derrida-Retaux model. So if you were to scale time in a nice fashion, scale space in a nice fashion, there is a good renormalization, and it is a process xt whose law satisfies the derivative in time of rho is equal to the derivative in space of rho plus the convolution of rho with itself minus rho. Okay, so there is just one problem with this partial differential equation, is that it's not conservative. If you start with a priority measure at time 0, you don't get a priority measure at all positive times. Okay, so there's probably something wrong with this partial differential equation. But okay, so what we want to do is to construct a stochastic process with a PDE whose density satisfies a PDE equation close to the one proposed by the physicists. Okay, so to do it, we really want to construct the Derrida-Retaux model as a process. And it can be done that way. So by saying, okay, so I define Fn as a CDF of the random variable xn. And to construct xn plus 1, I just add to xn Fn minus 1 of un plus 1, an uniform random variable, and I remove 1 when I have to remove 1. Right? So I construct the Derrida-Retaux model as a process. And then there is a very nice analogous in continuous time to that process, which is the following. So what you do is that you have a process xt that lose mass at rate 1 as long as excess is positive. And at exponential times, what you do is you add a copy of your process at its current value. Right? So I start from, let's say, x node equal 1. Then I lose mass at rate 1, so 1, 0.9, 0.8, until some exponential time, where what I do is I add to my process at that exponential time an independent copy of the process. Okay, so this is an analogous that we call the continuous time Derrida-Retaux model. Okay, and if we assume that this process exists, we can compute the equation satisfied by its law. And we show that actually this law, it satisfies the following partial differential equation in the weak sense, which is dt rho is equal to the derivative in spacing of indicator that x is strictly positive times rho plus the convolution of rho with itself minus rho. And this is a conservative function. So it's really, really close to the PD obtained by the physicists, but with some extra attention placed on the direct mass at 0 that builds when you lose mass, right? You lose mass until you hit level 0. So you have a positive priority to be equal to 0. And this is what makes the PD conservative here. Okay, so now how can we solve this stochastic differential equation to show that there exists a unique solution? Well, so what I can do is that I start with my random variable x node. And I know that x node will lose mass at unit rate. So xt is just x node minus t positive part until my first exponential time. So when I arrive at that exponential time, what I need to do is to construct an independent copy of xs. So what to do to construct an independent copy of xs? Well, I start with a random variable, x node prime, something like this, and I redo exactly the same construction, right? So maybe here I hit an exponential time before my my time xt, but then, well, I just need to add a new independent copies of the process at that time, and so start with a random variable x node second, add x prime 0 plus x second 0 minus those lengths, right, positive part, and I add them together. And so then I put the mixture, I lose mass at rate 1 again, and I construct my random variable x tilde t. So you can really do it, and the thing is that this construction, it stops. So you can, in finitely many steps, construct the random variable xt that way. And when you look back, what you see is that actually what you constructed is a Yule tree. So you can reconstruct the Derrida-Retaux process as a process on a tree, similarly to the Derrida-Retaux model in discrete time was constructed on a binary tree. So to construct the process at time t, what you need is to take a Yule tree of height t, and you start with ID amount of paint on the leaves of the tree that you sample according to the law of X node. So you do ID random variables on the leaves of the tree that represent amount of paint. And what you do is that at time 0, every painter starts from every leaf of the tree where they paint, and they paint down the leaves. They paint down the branches of the tree, right, using 1 unit of paint per unit of length. And when you have a branching time, well, the two painters, they put the remaining, the rest of the paint in common in one big pot, and they keep climbing down the tree. And so the quantity xt is just the quantity of paint that remains at the root of the tree.
Bastien, could I ask you?
Yeah.
Is it correct? So the previous slide and this slide, in the previous slide you are doing in the forward time, and you have more and more, and here it looks like in the backward time.
Yeah, so yeah, it's a very good observation. That here, what I did is that I construct my Yule tree starting from the leftmost side somehow, right? Whereas here, I construct my tree from the bottom up, and then I climb down the tree. So it's just a difference. Instead of looking at the tree from the leftmost side, I look at the tree from the root. And I make paint go down from all the leaves at the same time. So if you want, in discrete times, this would be the same as saying, okay, so what I do is that I construct an infinite binary tree, but I look at it from the leftmost descendant, right? Then you have this descendant, it has a parent and a brother, and then you look one step back, it has a parent who has a tree of height 2 below it, and you can climb up that way with more and more descendant added at each generation. So it's two different ways of looking at the same process. Okay. So so the good thing is that all those descriptions come circle, right? So there exists a unique weak solution to the SDE, which has the same law at time t as the tree paint scheme. And this is also the unique solution of the partial differential equation dt rho equal dx of indicator functions at x positive rho plus convolution of rho with itself minus rho. So you have a unique definition of the Derrida-Retaux model in continuous time, which is the family of rho t. Right? So now we can try to study this process and see if we can see if it can be easier to study the phase transition in this case. Okay, so the good thing is that the free energy again exists, but instead of normalizing by 2 to the n, you normalize by e to the t. And when the free energy is strictly positive, then xt divided by e to the t converges toward f infinity, so the free energy times an exponential distribution of parameter 1. Okay, so this is rather clear, right? This exponential distribution is just the growth rate of the Yule tree. So you know that, right? It's a kind of continuous time Galton-Watson tree. And if you look at the number of leaves at time t divided by e to the t, it converges toward an exponential distribution. And this is exactly what this exponential variable with parameter 1 is over here. It's just the growth rate of the number of leaves in your Yule tree. Okay, so I passed the proofs. And okay, something that we were not able to prove was that if the free energy is equal to 0, so if the expectation of xt is a little low of e to the t, then we strongly believe, but we were not able to prove that xt goes to 0 in probability. So it's quite easy to see that xt divided by e to the t goes to 0, but we were not able to prove that xt goes to 0 in probability. And another thing that would be nice would be to prove that if the free energy is equal to 0, then the law of xt conditioned on being positive converges toward the standard exponential distribution. sorry, not a standard exponential distribution, converges toward an exponential distribution with some parameter. And okay, so then the big open question would be to find the criterion on the initial distribution rho node that predicts if the free energy is positive or equal to 0. So this would be the analogous of this x node 2 to the x node smaller than the expectation of 2 to the x node. And we don't have this criterion here, at least not yet. Okay, so well, it seems that the continuous time version of the model is still too difficult for us. So we started to look for even simpler version of the continuous time version. And we found it by starting with an exponential random variable. So if the initial distribution rho node is an exponential distribution, then at all positive times, the low rho-t will be a combination of a direct mass at 0 and an exponential random variable. So actually, the low rho-t can be described by only two parameters, pt, which is the probability to be equal to 0, and lambda t, which is the tail decay of the exponential distribution, knowing that you're strictly positive. And this PDE can reduce to a system of ordinary differential equations. So p prime is equal to 1 minus p times lambda minus p, and lambda prime to minus lambda times 1 minus p. So note that if we were to use the original equation proposed by the physicist, we would have had p prime is equal to minus p times 1 minus p. Right, so the difference between the two is this lambda times 1 minus p. And so we have this nice properties that mixture of exponential variables and direct mass at 0 are stable under the action of the PT. So we can use it to reduce this partial differential equation into a finite dimensional system of ordinary differential equations. But when we have just one exponential random variable and a direct mass at 0, it becomes even simpler because you're in dimension 2, and you can find a preserved quantity of the system, an integral quantity of the system. So if you look at p over lambda minus log lambda, well, the derivative of h is equal to 0 due to the equalities of the system of differential equations. And also, it's quite natural to see that lambda has to be non-increasing because lambda prime is something negative, right? So I have a two-dimensional system of ordinary differential equations. I have a preserved quantity, and I know that lambda is non-increasing. So it means that I can draw the phase diagram of my system. So here it is, right? So what I did is I drew some curves of the form p over lambda minus lambda is equal to a constant. And I added an arrow saying that lambda has to decrease. So the solution pt lambda t has to follow those integral lines over here. And once you see this, well, then it's easy to decompose your phase space into three areas. So you have the subcritical phase, where you see that your integral lines, they bring you to the p equal 1 line. And p equal 1 corresponds to the place where xt is equal to 1. Xt, sorry, is equal to 0 with parity 1. So this is the subcritical area where the free energy is converges to 0. Okay. So now there is another area of interest, which is the subcritical area, where you see that actually p goes to 0 as t goes to infinity, and lambda goes to 0 as well. And lambda goes to 0 means that xt goes to infinity. So you're in the subcritical area where the free energy is strictly positive. And obviously, between the subcritical and the supercritical area, you have the critical line, so on which p goes to 1 and lambda goes to 1. Okay, so now we can study the asymptotic behavior of the solutions using standard techniques of ordinary differential equations. And what you observe is that if you're in the supercritical phase, then lambda t behaves as some constant times e to the minus t, and pt like t e to the minus t. So p goes to 0 really fast, as was I lambda. And the expectation of xt is similar to 1 over lambda t. So you see that the free energy will be equal to k. in the subcritical phase, what happens is that lambda t converges at exponential rate towards some number x larger than 1, and p goes to 0 also at exponential rate. So you see that in this case, xt goes to 0, but if I condition xt on being positive, xt condition of being positive converges toward an exponential random variable with parameter x. So you have this exponential distribution that appears naturally in that case. And when you're on the critical line, you can be really precise on the asymptotic behavior of lambda t and pt. And you see, for example, that pt behaves as 1 minus 2 over t squared, whereas lambda t behaves as 1 plus 2 over t. Okay, and you can do the computation as far as you want if you're patient enough. Okay. So now, well, what we can do is study the free energy of the differential equation as a function of P0, right? So I fix a lambda, and what I do is that I make P0 vary from 0 to 1. And what I observe is that there is this critical parameter PC, which is lambda log lambda minus log lambda, where I go from the supercritical area to the subcritical area. And what we are able to show is that the free energy behaves exactly as e to the minus c minus p to the minus a half as p grows to pc if the lambda at time 0 is larger than 1. The free energy behave as e to the minus p minus pc as well to the half if lambda is equal to 1, but then you have a polynomial correction over here. And if lambda node is smaller than 1, then actually the free energy behaves a little bit differently. Okay, so why is that true? Well, you see that this ordinary differential equation, it has a certain speed, and its speed is driven by 1 minus p. So if p is very close to 1, then the process moves really slowly. So now let's start with a lambda node that is larger than 1 and smaller than e. And what happens when p go closer and closer to pc? Well, you see that the top of the curve go closer and closer to the point 1, 1. And it will spend a lot of time in this area. So just analyzing what happens on this area allows you to study, to obtain a very good estimate on the asymptotic behavior of the free energy as p climbs to pc. And it is the same when lambda 0 is equal to 1, but instead of having a two-sided, right, you have, instead of having twice the amount of time to spend in the neighborhood of the point 1, 1, you only have half of the time to spend there. So this is why there is a little bit of difference there. And in the subcritical area, then it's a different picture. You don't get close to 1, 1. You get close to 1 lambda, which is why there is a different behavior there.
Excuse me, Bastien. It's been 35 minutes by now, so...
Oh, sorry. Yeah, okay. So just my last slide is to say that on the critical line, you can do computations as well. And you can, in particular, study the tree that you painted conditionally on that tree going all the way up to the root. And this tree has a very nice scaling limit. And we believe this scaling limit to be universal and to also hold in the discrete, for the discrete system. So it would be really interesting to study this critical tree. And okay, so I have plenty of open questions, but then thank you very much for your attention.